quantum computers use quantum bits called qubits, which can exhibit both 0 and 1 at the same time. But how? To understand this, we need to know about the principles that make atoms behave weirdly. Superposition. An atom can either be in an excited or non-excited state depending on its energy, but it can exhibit both states at the same time. However, when measured, it only gives one result, either excited or non-excited, like a coin spinning in the air, which can be both heads and tails, but shows only one result when it lands. Similarly, a qubit can also exhibit both 0 and 1, but when measured, it gives only 1. Next comes decoherence. A quantum particle will not stay in a quantum state forever, just like a spinning top eventually comes to rest after being affected by external forces. The time a particle remains in a quantum state is called coherence time. The longer the coherence time, the better the quantum computing. Even we humans wish for longer lifespans, don't we? In our PCs, 2 plus 2 is always done as 0010 plus 0010 in a 4-bit representation. But in a qubit, each qubit can be either 0 or 1, making 16 possibilities. If it behaves like this, then how can we work? That is where entanglement comes in. With entanglement, when one thing changes, all the others also change instantly. Because of this, we do not end up in a situation where the input data is changed randomly. Instead, we perform actions on all possibilities at the same time. Suppose x equals to 2, and y equals to 2, and z equals to x plus y. For a moment, if the qubits exhibit x as all ones instead of 0010, then in the third step, x will also remain as all ones, not some random zeros and ones. This keeps the algorithm consistent. If the algorithm is trying different possibilities and shows only one answer when measured, then how can we be sure the final answer is the correct one? Here comes interference. To understand this, imagine you throw 2 stones into a pond, one after another. Depending on the position of the second stone, the wave of the first stone can either collapse or increase. Similarly, quantum particles also exhibit wave-like behavior. Quantum algorithms are probabilistic. That means the algorithm shows the answer it thinks has the highest chance of being correct. A good quantum algorithm predicts the probabilities of all possible answers accurately. It then cancels out the wrong answers and increases the probability of the correct answer. This ensures that the correct result becomes dominant and is more likely to appear when measured. Since the algorithms are probabilistic, they are run many times. Each run provides a possible outcome. The high probability of correct results ensures that, after enough iterations, the answer can be confidently verified. We can then use classical methods or systems to measure correctness. For example, the RSA algorithm, which is used for encryption worldwide, is based on the principle that multiplying 2 big prime numbers to get a result is simple, but taking that huge result and converting it back into the 2 prime numbers is difficult. Even if we try brute force techniques by multiplying 2 prime numbers one by one, it will take hundreds of thousands of years. But with a quantum computer, using quantum principles, it cancels out prime numbers with less probability, while increasing the probability of the correct prime number. After a certain number of steps, it provides a high probability answer. We can run this algorithm many times to check if it keeps giving the same high probability answer. Once we fix the answer, we can multiply and check if the result equals to the original number. If it's correct, then we have cracked the RSA algorithm, which would take hundreds of quadrillion years to break using our PCs, in just minutes. If you understand this concept, then subscribe to the channel. Many such informational tech videos are coming soon.